All right, so go ahead and take your notes out. And let's see here. All right, where it says oxidation reduction. So it's right after the double replacement. Okay, there it is. So I'm not sure what page that's on. Oxidation and reduction. Somebody, 17? Okay. All right. So today what we're going to do, I'm going to talk about something that's pretty simple. And honestly, we've been doing it. You just haven't recognized or realized that you've been doing it. And these are actually reactions or things that take place within a single replacement reaction. And let's see here. Let's try to get to the quick part of it. When you hear me use the term oxidation and reduction, there's actually a saying. Let me find the saying here. Darn it. Oh, here it is. And I can't remember what page that's on. Probably around 18, 19. It says, Leo says Gerd. And when we talk about Leo says Gerd, it's just a way to help you remember what is actually happening. If I start off with, say, a metal, so like, for example, silver, that has no charge. It's solid silver. And then that silver gets a +1 charge. What has happened to cause that to become more positive? Has it gained an electron, lost an electron? Lost an electron. So we would put it on this side of the equation. Now, these are that's what's called a half reaction. In other words, for the silver to lose an electron, it has to be willing to give that electron to somebody else. So generally speaking, there might be another metal on the other side, like, I don't know, sodium all by itself. And so what's going to happen is that sodium had a +1 charge over here, and so it would need to gain that electron, and I'm kind of crunching everybody up here, gain an electron to get it to go from a +1 charge to no charge. And what has happened is that sodium has actually become more negative. How? Because over here, as it stands alone, it only has, I think it's 10 electrons, so the same electron configuration as helium. If it gains one more electron, now it has all 11 of the electrons. So here, sodium +1 is being what? Oxidized or reduced? Gaining electrons means that it's undergoing a reduction. So we'll always have two half reactions within a whole reaction. And this actually takes place in all the single replacement reactions. And in some cases, the metal is going to say, no, I don't want to give up an electron, because I like my electron. And that's what that activity series table helps do for us. So when we look at these types of reactions, one metal is going to give away an electron, the other one's going to take it. Now, let me ask you this. Were there any blanks that I skipped over to get to that? Sorry, let me go back to that. So were there any there? No, good. There. The half reaction. So past this. Okay, and I'll do this demo here with a different metal. Here it is, half reaction. Okay, so oxidation. So again, whenever an atom or an ion becomes more positively charged, we're saying that that is undergoing an oxidation. Undergoing an oxidation means that it's losing an electron, becoming more positive. And then if something is becoming more negative or gaining electrons, we say that it's undergoing a reduction. And there's the half reaction that I just demonstrated there. Okay, so those two blanks. Okay. All right, let me see here. Any other blanks here? Net equations for the redox equations. We'll do that here in a moment, so just get the blank here and that'll make sense once we do them. I know that you can read that when you get your free time. Okay. So everybody have that blank number of electrons. And what this statement is saying is that once we balance these out, and we'll do this during the reaction, that if, say, something gives up 2 electrons and, say, a metal only wants 1 electron, then that means we're going to need 2 of those metals to accept both of those electrons. And we'll demonstrate that here in a moment. then this is me going through the process, which I'll do here shortly. And we'll talk about the agents. Actually, I may not talk about agents, but go ahead and get the blanks. We talk about them in AP. Okay. Actually, I'm not going to talk about agents in here for you guys. Okay. And then we'll do some of the practice problems here. But before I do that, I want to, does everybody have those blanks? Yeah. Okay. I'm going to do a demo. And turn to the page where you have the single replacement table. And we'll see here. Okay, I'm going to work with iron and some copper 2 sulfate. All right, now good practice for the quiz today. What type of reaction is that? Single replacement. And who is going to try to replace whom here? Okay, will this take place? Yeah. Okay, so on the product side, what are we going to form? And iron can either be a 2 or a 3 charge, so I'll leave it up to you. A 2 charge what? What do you mean it's even? You mean even like 2 is even and 3 is odd?
Like, yeah, like the 2 and the 4 kind of.
What's the charge on sulfate? -2. So that's why we would want to use iron +2, just to make it easy, right? So if iron has a +2 charge, then we have +2, -2. And then who's going to be kicked out? The copper. All right. So this will take place, and it's balanced. Atoms, charges, all that good stuff. All right, let me turn the lights on so you can see this. Here, I have a blue solution, kind of looks like blue Powerade. It is not blue Powerade. It is actually copper sulfate. The reason why this is a bluish color, I should hold it up. The reason why it's a bluish color is because the copper ions are blue. And here, I have an iron nail. It's a nail just from construction sites. Bought a box of them. It's pure iron. So if I take this iron and I place it in this copper sulfate, what should I see appear? Well, the iron sulfate, if I were to ask you if that's soluble or not, you could look that up real quickly on your double replacement sheet. You would find that, yeah, that is soluble. But we should also get some solid copper. Here we have our copper sulfate solution. I have the iron nail. So if I place this nail in the copper sulfate, what should happen? Well, we have pure iron. That's what the nail is. So we have our pure nail, or our iron nail, and I'm putting it in this copper sulfate, which is, actually it's dissolved of copper ions and sulfate ions. The copper is what makes this blue.
Is the nail going to dissolve?
Is this nail going to what? No, there's no explosion. It says it right here.
It's going to turn blue.
No, it's not going to rust. What should we see on the nail? Copper. So copper metal, right? And what color is copper metal? No, it's not copper blue. It's copper colored.
It's like that's rusty.
That's not rusty.
See? I can't hold that far. Copper is a rusty color.
Copper is copper colored.
It's like a rusty color. It's like a rose color. I was right.
Copper colored.
I said rusty. It's like a orange.
Nobody gets out and looks at copper anymore. Here, for the viewing audience, copper is copper colored. Rust color? Rust is reddish.
It's red brown. Orange brown.
Okay, copper colored. Good. But, and I know you may not be able to see it from that far back, but this is silvery looking. This is coppery looking. There's what? No, there are not copper ions in blue Powerade. Ugh, that would be bad. So, that's our reaction. So let's talk about the half reactions that are involved here. And when we look at this reaction, let me erase those arrows there. Okay. Let me ask you this. What is the charge? Should have scrolled that down. What is the charge on the iron all by itself? Right here, this iron. Okay, let me ask you a question. Luke, when you're by yourself, should you ever be excited? It's not a trick question.
Yes.
No.
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 He told me to say yes. He kept saying yes.
No. So when you're by yourself, you have no charge. There's no excitement going on, right? It's only when you hook up with somebody that you're allowed to get excited.
Oh, you're not that kind of excited.
No, I don't know what kind of excited you're talking
No,
about.
that is a trick question. I did not know that you meant that kind of excited, because that's excited. That's not excited.
Look. I meant like having a good time, like laughing and carrying on and joking with somebody. I'm not saying you shouldn't be laughing at yourself, right? Or joking around with yourself. So whenever something's all by itself, or even, let's put that out there, okay? Iodine, remember how it ends in INE? Let's pretend that iodine is with its twin. Shouldn't be excited when you're with your twin, right? It's got to be somebody else. No. All right, so let's come back over here. What's the sulfate's charge? -2. And copper has a +2. Okay, +2 because it's with somebody. All right. What's the charge on copper over here?
+0.
Very good. Should have no charge since it's all by itself. Okay. What's the charge on, well, we know sulfate's -2. So what's the charge on iron? +2. All right. So here's what's happening. We have, let's do these half reactions here. So we have iron that has no charge is going to iron, and I'm only going to look at just the atoms itself. Iron with a +2 charge, right? So iron has no charge, goes to a +2. Agree? Good, okay. And the other scenario is I have copper with a +2 charge going to copper with no charge. Would you agree? Good, okay. So how did iron go from no charge to a +2 charge? Did it gain or lose those negatively charged electrons? Lost, very good. And so if I'm losing electrons, am I going to put it on this side, the left side, or the right side? If I'm going to write down where the electrons go for the iron, because it lost 2 electrons, do I put it on the left side or the right side? The right side. And here's something that's kind of easy to remember. Since the electrons have a negative charge, okay? -2, what's the charge on the iron? +2, okay, so make sure you're saying plus and negative. So +2 minus 2 equals what? 0. So the charges need to be the same on both sides. So if copper has a +2 charge over here and a 0 over here, what side do I put the electrons? The left side. And how many do I put? 2. Okay. So when we look at this, we want to make sure that our electrons are equal in both half reactions. And in this case, we have 2 there and 2 there. That's awesome. And in your history of taking chemistry, how many times have you seen electrons in an overall balanced equation? 0, and you're not starting today. So what we want to do is we want to cancel out any alike terms, okay, and then we'll bring everybody else down. Now, let me ask you this. Copper ions are different than copper metal. Is that true? Yeah. I mean, if you look at it, copper ions are blue, where copper metal is rust colored. No, copper colored, okay? So they're very different. In other words, I can't see any solid copper in here because they're copper ions. But here I can see copper because it's kind of brownish copper color. All right? So they're very different. So if it has a charge, it is different. So we can't say that we can cancel out the coppers because they're not the same. So we'll bring everybody else that's down. Okay, and it doesn't matter what order you put it in, just as long as it's on the respective side. Okay. And what I just did was I wrote the half reactions for each of these, and then I wrote the total reaction. This is what we would call the net redox reaction. Here's a couple things we need to check. Make sure we have the same number of atoms on both sides. I have one iron, good. One copper, good. And then the last thing I want to do is check charges. So iron has no charge, +2, so the overall charge on the left side is +2. Add 0 plus 2 equals +2. So my number of atoms are balanced and my charges are balanced. This is my answer for my redox equation. Isn't that easy? Pretty easy, yeah. The solution before and after. Now, as in the video before I worked out the redox equation, this is how the copper 2-sulfate solution looked, and the iron nail. Obviously, you can see that the iron nail looks kind of a silvery color on that. And so what has happened when you place that nail into the copper sulfate, and again, we can do that rather quickly. As I place that nail into the copper sulfate for a few seconds, you can start to see it darken a little bit in there. And we bring it out, it definitely has a change in color. If you take a look at the top half versus the bottom half actually has that copper coating on it, where the top half, which was not exposed to the copper sulfate, is still that silvery looking color. And that's the color that iron really is when it's not oxidized. When you see it as a black color, that's mainly the paint and other things have been done to it. However, I left the nail in overnight on the original solution, and when we come over here, you'll notice that the colors of the two solutions are drastically different. Also, what you may notice around the nail is that there's this big fluffy stuff around it. Well, that big fluffy stuff is actually pure copper, and that's how much copper was actually in the solution. So when we look at that, that is all pure copper that has actually switched places with the iron that was in the nail. Now you also notice that the color of the solution went from this beautiful aqua blue to this kind of yellowish greenish color. What can you speculate about the color change? Well, hopefully you remember from when I did the demo that the blue is representative of the copper ions. And if you take those copper ions out of solution, what you're left with is the copper metal that's actually on the nail itself, because it replaced a single replacement reaction, replaced that copper ion into pure copper. And what we're seeing left over here is kind of the iron ions that are in the solution. And there's still some copper in there. It gives it a kind of a bluish tint, but iron has a much different color than the copper ions. So I wanted to include this in the video showing the difference between the two solutions before and after. And again, looking at the nail, just as we put it in just for a few seconds here, not even a whole lot, you can tell that there's something that's actually taking place there. So let's do another one. Okay. Let's look at this one in your notes. Okay. Where you have lithium, and I didn't even include the non-metal in this. Okay. So we have lithium and lead +2. So let's scroll that down. So we have lithium and lead with a +2 charge. And it says that we go lithium +1 and lead all by itself, right? Okay. Let's pick a half reaction. Which one do you want to start with? Lithium or lead? And it doesn't matter. Lithium? Okay. So we'll do lithium. And what's the charge on lithium over here? 0. Good. And the lithium on this side has a +1 charge. So if you want to write the 1, that's fine. And then the other half reaction looks like this, where you have lead plus 2 going to lead, no charge. Okay. So let's balance the half reaction. So with the lithium, how many electrons did it gain or lose to go from no charge to a plus 1? 1. And what side am I putting the electron on? The right side. Again, what I want to do is I want to balance charges. So -1 plus 1 equals 0, right? Okay. And then looking at the other, what do I do? I'm going to put 2 electrons over here, right? Okay. So again, I want to make sure that this half reaction is balanced. So -2 plus 2 equals 0. All right. Now we've got something interesting. Do we have the same number of electrons on both sides? No. How can we do that? We multiply the top by 2 and the bottom by 1. Well, you don't need to multiply the bottom by 1. So now I have the same number of electrons, and we have to make sure our electrons are balanced out before we do anything else. So the electrons are now able to cancel. And what will my finished reaction look like? It'll be 2 Li, right? 2 lithium with no charge, plus what? Lead plus 2, and there's only one of those, okay? And then it'll be, again, remember your parentheses, so 2 lithiums with a plus 1 charge, and do include the charges. You have to include charges, because if you don't include the charges, then they're the same on both sides and they cancel out. And then lead with no charge, okay? So let's check. What's the total charge on the left side? So 2 times 0 is 0, plus 2. And then 2 times plus 1 plus 0 is 2. Do we have the same number of atoms on both sides? Yeah, isn't this easy? It is. It is not on our quiz today. Yep. I know, it'd be easy points, I know. All right, let's do one more. Okay. Actually, yeah, one more of these. Let's do 2A. Okay, this isn't your homework, but let's go ahead and do 2A. Chromium plus 3 and zinc. Okay. Chromium, what did I say, plus 2? 3, thank you. 3 and zinc. And it will make chromium no charge and zinc plus 2. Is that right?
Yep.
Okay. All right. So let's look at the half reactions. Which one do you want to do first? Chromium? Okay. So chromium plus 3 going to chromium, no charge. Let's just cut to the chase. Where are the electrons going? Left side. Very good. And how many? 3. Very good, because there's no charge here. So that means we need 3 electrons. Okay? And then, so is that okay? Yep. Then looking at the zinc, how many, whoop, 2 there. So, electrons, and where are they going? The right side. And as a heads up, electrons will never be, in the 2 half reactions, electrons will never be on the same side. Okay? Somebody has to be giving away the electrons, and somebody has to be accepting the electrons. Okay? So in other words, zinc, is it giving away or taking electrons? Giving away, very good. It's losing. Therefore, the chromium can gain those electrons. Do we have the same number of electrons on both sides? Nope. So we need to multiply them up. So we're going to multiply the bottom by 3 and the top by 2. So the electrons are gone. And then, how would this look? 2 Cr plus 3, good, plus 3 zincs, no charge, plus 2 chromium, no charge, plus 3 zinc, plus 2. Okay. Charge on the left side? What's the charge on the left? Plus 6. So 2 times 3 plus 0 plus 6. Charge on the right, 3 times 2 plus 6. Are we balanced? Charge or atom wise? Yep. Awesome. Okay. So those are pretty easy, right? Turn ahead to oxidation numbers. And honestly, we've already talked about oxidation numbers. What are our oxidation numbers? The charges. Okay, it's the charge on your periodic table. So when you look at your periodic table, for you guys, it's the little numbers in the top right-hand corner. Okay, those are the oxidation numbers. So in some cases, some elements have more than one oxidation number. In a lot of cases, some elements just have one oxidation number. Okay, so oxidation numbers are the potential charge that an element may have when it's with somebody else. Okay, so like for example, I put on there a parent charge, but it's the possible charge that it could have. So when I'm asking you to find oxidation numbers, now we can start to look at, say, okay, so when we start looking at oxidation numbers, now we can start messing with, say, oh, I don't know. Let's look at nitrogen. Where's nitrogen at? Look at that. Nitrogen can either be +1, -1, +2, -2, +3, -3, +4, or +5. That's a lot of charges, right? It could be any of those. Okay, that's why those charges are there. However, if it's the only nonmetal, if nitrogen's the only nonmetal in the compound, what charge is it? -3. Okay? And oxygen only has a -2 charge that we care about, and fluorine only has a -1. But once we start to get down here, now chlorine, sulfur, they have multiple charges. So when you're going and finding out or determining the oxidation numbers, the last thing you want to do after you finish determining it is check and see if it's a legal oxidation value. All right, and so that's what we're doing with this. So here's a neat way to determine the oxidation number. So here I have a compound of sodium phosphate. Let me blow it up. It's sodium phosphate. And I want to know, what is the oxidation number for the sodium, what is the oxidation number for the phosphorus, and the oxidation number for the oxygen. Here's how you do it. You have your compound. Oops, let's use a different color. We have Na3PO4. Okay, that was given to you. The best way to do this is line them up, like Na, phosphorus, and oxygen. And then I want you to tell me how many of each are in the compound. How many sodiums do we have in that compound? 3. So I have 3 of those. How many phosphorus do I have? 1. How many oxygens do I have? 4. Yeah. Now what's nice about some of these compounds or some of these elements is that they're always the same charge. Okay. Make it a little smaller. Okay. So when we look at, say, I don't know, oxygen, what's the charge on oxygen every single time? -2. So when you go, whoops, we don't want that. So when we look at oxygen, we can say that, okay, oxygen has a -2 charge. Okay. Looking at the sodium, what's the charge on sodium? Get over there. So sodium's always a +1 charge. So some of these are like dead giveaways where they don't ever change. So we have a +1. Okay. Now, what's neat about this whole compound has a total charge of 0. In other words, the algebraic sum of all these elements add up to equal 0. So we want to make sure that our total charges equal 0. So what is 4 times -2? -8. Good. And what is 3 plus 1? Or I'm sorry, 3 times +1? +3. Okay, so here's the kicker. We want to find, excuse me, some number here that when we add it to +3 and -8, it equals 0. +5, right? So we'll put a +5 there. And how many phosphorus do we have? 1. So that means all these phosphorus exhibit a +5 charge. Here are your oxidation numbers. Now let's check. We know that sodium has a +1, oxygen has a -2. Does phosphorus have a +5? 5. Phosphorus, there you are. Plus or minus 3 and a plus 5. That's good. Okay. Let's do one more. Okay. These are the oxidation numbers right here. These are the numbers that you'll find on your periodic table. These are just charges to help you get the oxidation numbers. Okay. Do one more here. Let's look at, we just did copper sulfate. Okay, let's do copper sulfate again. So we have CuSO4. Okay, so let's line them up. We have copper, we have sulfur, and we have oxygen. How many coppers do we have? 1. How many sulfurs do we have? 1. How many oxygen? 4. And we know that all those have to add up to 0. What's the charge on oxygen? Minus 2, negative 2. So all the oxygens exhibit what charge? Negative 8. All right, now it gets interesting. Because copper can either be a +1 or a +2 charge. So in that scenario, what we need to do is look at our non-metal. So when we look at our non-metal, which in this case is sulfate, we know that sulfate, SO4, has what charge? Negative 2, very good. So if we know that sulfate has a negative 2 charge, what must the charge on the copper be? There you go, it's a +2 charge. So we used the non-metal to help us tell what the charge on the metal is. So therefore we have a +2 charge. All right, now we need to figure out what is the charge on sulfur. So what numbers, when we add all those together, equals 0? +6. And then we have to look and see, is a +6 an option for us for sulfur? Right there. Okay. So when you go through this process, and again, there's more than one way of doing this, but this seems to be the easier of the processes. Once you finish, check your periodic table and say, is that a legal charge? And if it is, you did it right. If not, you might want to go back and check and see what you did. All right. Do we need to work any more of these out? No? Really? Yes, yes, yes we do, or no we don't?
No, we don't really.
Think we're good?